Hello everyone, myself Alpesh Patel and today we discuss the numerical part for whirling speed of the shaft. Before starting the numerical part, let's write all equations which will helpful to us. Figure shows a shaft which is subjected to a point load W at a distance A from the left side bearing and distance B from right side bearing. Shaft is supported by the bearings. If shaft is held in a short bearing such as roller or ball bearing, then it is equivalent to simple support, and a deflection, static deflection, can be calculated by this equation: delta equal to W into A square into B square divided by 3EIL, where I is a area moment of inertia, pi by 64 d raised to 4, E Young modulus, and L is the length of the shaft. If shaft is held in a long bearing such as general bearing, then it is equivalent to fixed support, and value of static deflection can be given by this equation: delta equal to W into A cube into B cube divided by 3EIL cube. If weight of the shaft is considered, then deflection of the shaft delta S equal to 5W L raised to 4 divided by 384 EI. Here we consider UDL is applied on a shaft of amount small w per meter length. Natural frequency in radian per second omega n can be calculated by this equation: omega n equal to square root of g divided by delta plus delta s. Delta is a static deflection because of the point load, and delta s is a deflection of the shaft because of the weight of the shaft. Natural frequency in RPS can be calculated by this equation: NC equal to 0.4985 divided by root delta plus delta S. When shaft is rotated with the angular velocity omega, then net deflection of the shaft can be calculated by following equation: y equal to E omega by omega n whole square divided by square root of 1 minus omega by omega n square whole square plus 2 zeta omega by omega n whole square. If there is no damping force in the system, or if damping force is neglected, then the deflection of the shaft can be calculated by following equation: E into omega by omega n whole square divided by 1 minus omega by omega n whole square. Let's start problem 1. A rotor of weight 50 Newton is supported in a bearing 400 mm apart. The diameter of the shaft is 20 mm. Due to the manufacturing errors, the center of gravity of the disc is 0.1 mm away from the midpoint where the shaft is introduced. The shaft rotates at 4500 revolution per minute. Determine critical speed, maximum amplitude of steady state vibration considering weight of the shaft. The shaft is horizontal, supported, and support condition may be assumed to be simple supported. Assume the density of the shaft as 8900 kg per meter cube. Take Young modulus 1.96 10 raised to 11 Newton per meter square. So given data are capital W 50 Newton, which is at the midpoint of the shaft, length of the shaft 400 mm 0.4 meter, diameter d 20 mm 0.02 meter, eccentricity 0.1 mm, it means 0.0001 meter, angular velocity 4500 rpm, density of the shaft is 8900 kg per meter cube, and Young modulus 1.96 10 raised to 11 Newton per meter. First calculate area moment of inertia capital I, that is given by pi by 64 d raised to 4. The value is 7.89 10 raised to minus 9 mm raised to 4. The first question is critical speed. Critical speed of the shaft can be calculated by this equation, root g by delta plus delta s, where delta and delta s are unknown. The shaft is simple supported and point load at the center. Deflection can be calculated by this equation, W into a square into b square divided by 3EIL. Now substitute the value of A and B equal to L by 2. We get delta equal to this, and if you substitute the value of W, L, E, I, we get 4.33 10 raised to minus 5 meter. Now weight of the shaft need to calculate, as density of the shaft is given. Weight of the shaft per meter length is equal to density into cross section area into length of the shaft 1 meter into G, that is equal to 27.42 Newton per meter. Delta S, because of the weight of the shaft, is calculated by this equation, and finally we get the value 5.9 10 raised to minus 6 meter. Critical speed of the shaft is equal to 446.47 and 4263.48 rpm. Next question is maximum amplitude of steady state vibration when shaft is revolved at 4500 rpm. So deflection of the shaft can be calculated by this equation, where E is the eccentricity, omega is 4500 rpm, and if you substitute all value, finally we get deflection of the shaft is equal to minus 9.252 10 raised to minus 4 meter. The negative sign shows that deflection is in reverse direction. Next problem, vertical steel shaft 15 mm diameter is held in long bearing. Long bearing means support is fixed support, 1 meter length, and carries at its middle a disc of mass 15 kg. So point load is 15 kg at the middle of the shaft, diameter 50 mm, 1.5. The eccentricity of the center of gravity of the disc from the center of the rotor is 0.3 mm. The modulus of elasticity for the shaft material is 200 giga-Newton per meter square. That is Young modulus. Permissible stress is given by 70 mega-Newton per meter square. Questions are the critical speed of the shaft, and second, the range of the speed over which it is unsafe to run the shaft. Neglect the mass of the shaft. So we just write down given data: diameter, length, mass, eccentricity, Young modulus, and permissible stress. So first question is critical speed of the shaft, that is calculated by this equation, square root of G by delta plus delta S. Here mass of the shaft is neglected, hence delta S equal to 0. Since shaft is held in long bearing, therefore it is assumed to be fixed at both ends, and hence deflection is given by this equation. Substitute the value of A and B equal to L by 2. We get deflection equal to W L cube by 192 EI, and that is equal to 1.5 10 raised to minus 3 meter after substituting all values. Natural frequency of transverse vibration, that is nothing but the critical speed of the shaft in radian per second, calculated by this equation omega n equal to root G by delta plus delta S. And finally we get the answer 772.25 rpm. Second question is the range of the speed over which it is unsafe to run the shaft. Let N1 and N2 equal to minimum and maximum speed respectively. When shaft starts rotating, the additional dynamic load, that is W1 equal to M1G, is acting. Let's apply pure bending theory. M by I equal to sigma B by Y. M is a maximum bending moment. It's nothing but the W L by 8 point load at the center with fixed support. I pi by 64 d raised to 4 sigma B bending stress. Y is a d by 2 distance of most outer fiber from the neutral axis. And if we substitute all these values, finally we get m1 equal to 19 kg. Now additional deflection because of this 19 kg mass is nothing but the m1 into delta by m. The delta is nothing but the deflection of the shaft because of the mass 15 kg. And finally we get additional total deflection is 1.9 10⁻³ meter. This is nothing but the y. Deflection of the shaft when shaft is running with certain speed. Now deflection of the shaft when there is no damping force is given by this equation, y equal to plus or minus e omega by omega n whole square 1 minus omega by omega n whole square. Here y is nothing but the 1.9 previous answer, and convert this omega into RPM, we get this equation n by nc form, and substitute the value of y, substitute the value of e, substitute the value of nc. We can find out two speeds n1 and n2 from this equation. Finally n1 equal to 718 RPM and n2 equal to 843 RPM. Keep in mind that critical speed is around 772.25 RPM. So this is the range of the shaft RPM 718 and 843. In this range, the stress induced in the shaft member is higher than the permissible limit. That is the answer. Thank you.